Our next speaker is Alison Fout, professor from University of Illinois, Urbana-Champaign. And she's going to be talking about cobalt-catalyzed parahydrogen induced polarization. So whenever you're ready, please take it away, Alison.
Thank you for the organizers for inviting me. And I have to apologize. I came into my office because I have two small children that tend to interrupt every single meeting. And now all of a sudden today they're doing construction. So I apologize if you hear noise in the background. But I'm very excited to share with you some of the work that my group has been doing. We are a synthetic inorganic group, and we are very much interested in developing new catalysts for parahydrogen-induced polarization. And so looking at things like the rhodium and iridium catalysts that we have heard about so much during this conference so far, my group really wants to think about sustainable catalysts. And so moving from rhodium and iridium to something like cobalt, one of these first 4 transition metals, we were curious if we could then develop new cobalt catalysts for PHIP. In taking this, though, we realized that you just can't take any cobalt catalyst off the shelf that may do hydrogenation chemistry. It needs to have some specific requirements. And so we thought that in order to engender reactivity like rhodium or iridium, especially rhodium and hydrogenated PHIP, the catalyst needed to be diamagnetic and likely stay diamagnetic throughout the entire catalytic cycle. And so in this regard, then, we would be targeting cobalt-1, cobalt-3 catalytic cycle to go from a cobalt-1 species to a cobalt-3 dihydride that would be definitely necessary for hydrogenation type reactivity. This catalyst also needed to be hydrogenated if we're looking at Altadena or Pasadena type PHIP experiments. But if we were doing SABRE, then that wouldn't necessarily be a criteria. Furthermore, we would have to observe pairwise transfer of hydrogen to the substrate. And so just because a catalyst actually can do hydrogenation, it doesn't necessarily mean it would be a good PHIP catalyst. And I think this was recently shown in the work by Dinopoulos, where both of these complexes shown here, this DPPE ruthenium tricarbonyl, as well as the iron DPPE tricarbonyl species, both of them were very good hydrogenation catalysts. However, only the ruthenium complex showed the pairwise transfer of parahydrogen and any PHIP type polarization. And so the iron complex, albeit a hydrogenation catalyst, didn't do that pairwise transfer that would be necessary for this type of reactivity. And so furthermore, we would like to see good functional group tolerance for our substrates. That way we can access a variety of substrates with our cobalt catalyst if we want to ever use this for really anything. And then we would also ideally like to see polarization transfer to C13 nuclei of a carbonyl or N15 nuclei, like many have shown throughout this conference. And so in order to initially engender this idea of a diamagnetic species, my group is very much interested in ligand design and how we can influence a metal's reactivity based on the ligands that really surround it. And so here we use the CCC ligand platform shown here. So this has a central anionic coordination to the metal center that would sit right here in this pocket. And so upon deprotonation of the aryl ring, it would be anionically coordinated, it would be electron rich, and allow us to engender metal 1 species. Furthermore, it has on these carbenes, these benzimidazoles that can avoid abnormal carbene formation. And so what abnormal carbene formation is just when upon formation of the carbene, the actual carbons in this backbone actually spin around and bind to the metal center in this pocket. And so while it's not preventative of any catalysis, it's just not ideal because your catalyst and your ligand could be changing throughout the process. Furthermore, this also helped us ease the ligand synthesis, and it's a much easier to synthesize with these aryl moieties in the backbone. Next, this ligand has these flanking aryl groups that we can actually really tune. You can see that compared to some of the other catalysts that have been used, especially the rhodium and iridium catalyst, this is a very bulky ligand. And so we may need to pare back what's actually flanking the metal center to either increase solubility, change the steric profile, prevent any dimerization. And so having the ability to tune these is really key as we move on in these catalytic studies. And so we've been able to successfully synthesize cobalt-3 complexes. So this one shown here, which is a cobalt-3 dichloride with a pyridine bound. You can take this species and you can reduce it with really any reductant to get to a cobalt-1 complex shown here. That can then be reoxidized to the cobalt-3 with 2 equivalents of oxidant. And so here this showcases that we can access a cobalt-1 and a cobalt-3 species, which is really ideal for our catalytic studies. I just like to show the colors of these molecules because I just think they're really beautiful. The cobalt-3 is this green color, the cobalt-1 is a red, and then the paramagnetic cobalt-2 complex is actually yellow. And so by adding our appropriate equivalents of reductant or oxidant, we can access the cobalt-2 species here. And so knowing that we can do cobalt-3, cobalt-1, and even access cobalt-2, we were very curious about the reactivity of this complex with dihydrogen. Clearly, if we're going to do PHIP chemistry, we need to see the reactivity with dihydrogen. And so we took our cobalt-1 dinitrogen complex that actually has a triphenylphosphine bound and reacted it with H2. And what we observed in the proton NMR spectrum was that an H2 resonance consistent with the formation that consistent with the addition of H2, as well as a new resonance around negative 5.5 ppm. You can see it's relatively broad. And so we were unsure if this was actually a cobalt-3 dihydride, which would be key for hydrogenated PHIP, or if this was actually just a cobalt dihydrogen complex where the H2 had displaced the bound dinitrogen. Doing T1 studies, we were able to determine that the T1 is 12 milliseconds, which is consistent actually with the formation of a non-classical dihydride. So here the dihydrogen actually just bound to that cobalt center and actually didn't cleave that HH bond. And so we wanted to understand this a little bit further and see if this actually HH bond was relatively activated, just not fully cleaved on the NMR timescale. And so we reacted our cobalt-1 complex with HD gas, and we were able to form the HD species shown here. The coupling constant is around 32.5 hertz, and you can see that now manifested in that resonance around negative 5.5 ppm. And so using this complex, we were able to compare it to the other well-known cobalt-1 dihydrogen complexes, well-defined, I should say. There's several dihydrogen complexes in the literature, but they're not as well-defined to Heineke and Peters. And using the T1s, as well as the coupling constants that we got from the HD species, we're able to determine that the HH bond actually isn't that elongated at 0.88 angstroms. We were able to back that out from Morris's equation. And so if this were almost activated, you would imagine an HH bond up around 1 angstrom. And so this isn't that close to cleavage. But my student had noticed, Keenan Tuckmick, something very interesting in the proton NMR when he did the HD reaction. He actually noticed the formation of H2. And so he went back and did the reaction of the cobalt-1 species with a half an atmosphere of H2 and half an atmosphere of D2. And what he observed is the fact that he formed the cobalt HD species again. And so therefore we have H2-D2 scrambling going on, consistent with cleavage of an HH bond. You can see that both here in the proton NMR spectrum, where you now see HD gas being formed in the triplet around 4.4 ppm, as well as the expected H2 in this proton NMR spectrum. And we also see the appropriate coupling that we would expect for the HD complex. And so now this was exciting because now we know that actually we can cleave an HH bond, and perhaps we can start to look at hydrogenation chemistry with this species. However, when we looked in the literature and really wanted to understand, has cobalt been demonstrated to do well-defined cobalt complexes for hydrogenation chemistry, we discovered that these species actually had not been reported for any types of catalytic hydrogenations. And so even though actually Peters did report some HD scrambling, he did not report any hydrogenation chemistry. And so we were curious if our molecule could actually do any hydrogenation. And we started off with the simplest reaction of just looking at alkene hydrogenation. And so what we did was we took an olefin, reacted it with our cobalt catalyst at 2 mol% in deuterated benzene with addition of 4 atmospheres of H2. And we were able to cleanly form the alkane relatively quickly, in some cases in less than 2 hours. We were able to isolate all of the olefins shown, the saturated olefins, the alkanes shown here, in really good yields. And we can actually tolerate some steric bulk on this catalyst despite having such a large ligand. The only thing that we actually struggle with a little bit with this ligand system is actually internal alkenes. So shown here in the cyclic cyclohexene, you can see that we had to heat this up at 60 degrees C to actually convert it to the hydrogenated product. But what's really interesting for us, and what my group really does like to do, is understand mechanisms. And so this is where we really want to explore this hydrogenation catalyst a little bit more. So we know it's diamagnetic, we know it does hydrogenation, but does it do pairwise transfer of parahydrogen to a substrate? And so we probably naively went into this thinking, oh, we could add parahydrogen and show that if it just bound parahydrogen but wouldn't really cleave it and go through a cobalt-2 and was maybe doing a sigma type mechanism, then we would see no polarization effect in our NMR. However, if we were accessing a cobalt-3 where now the hydrogens were magnetically inequivalent, then perhaps we could see this cobalt-3 in our NMR spectrum. Unfortunately, we could not observe any cobalt-3 complexes or actually in our NMR. And so my student Keenan actually went through and did the reaction like it probably should have been done, where he did it under catalytic conditions. And so if you take our catalyst and we add parahydrogen in the presence of styrene, we see we were able to obtain this proton NMR spectrum here. This is the OPSI NMR spectrum, where we observe where the parahydrogen has added, so to the styrene, so the ethylbenzene is formed here in these resonances around 1 and 2.5 ppm. What was also interesting is we observe resonances for the free styrene up between 5 and 7 ppm, likely indicative of maybe that this is SABRE and that we were binding the olefin and then it was popping off. And so with this, and actually a lot of some deuterium studies, we were able to use parahydrogen to really tease out the mechanism for our olefin hydrogenation. And that was very useful for us. And so we think the mechanism of this reaction is that the cobalt-1 species binds dihydrogen. The dihydrogen, upon addition of the olefin, the dihydrogen actually gets cleaved to form a cobalt-3 dihydride. That then undergoes insertion of a hydrogen into the olefin to form the cobalt-3 alkane dihydrogen species. This is a reversible process. Deuterium labeling show that we did see incorporation of the deuterium in both positions. And then upon reductive elimination, we form our alkane and reform our cobalt-1 catalyst. So parahydrogen really helped us kind of tease out that we were accessing a cobalt-3 and that the entire catalytic cycle likely remained diamagnetic. However, we showed with the olefins that we had decent functional group tolerance, but we would like to see a lot more substrates that could be accessible. And so in order to do this, we looked at Alkyne hydrogenation. And so here, again, we added an alkyne with our cobalt catalyst and varying from 2 mole percent, around 2 to 5 mole percent with 4 atmospheres of hydrogen. And we just kept this. It was, when we started this, it was actually summer. So we wanted to keep everything at a decent temperature, and it was 30 degrees C. And what we discovered is that we obtain a variety of products where it's E-selective. So it's actually the trans product where the hydrogens have added trans to one another as opposed to the cis. And you can see that the E to Z ratio is really greater, or really good, greater than 99% in most cases. And so we're very selective for that trans product. You can also see on this table that we have a pretty large substrate scope, and now we can really tolerate a variety of functional groups. And so this is really nice, and it will hopefully open the doors for future studies where we want to tolerate more substituents, more functional groups, so on and so forth. But again, one of the questions that my group had was, what is the mechanism for this? You can imagine that we could be doing transhydrogenation to get to the E-selective product shown here. But you could also imagine that we could be doing cis-hydrogenation and then have a very good trans-isomerization catalyst. This pathway makes a little bit more sense for cis-hydrogenation and trans-isomerization based on the first row transition metal. But we were curious, and once again, the addition of parahydrogen helped us tease out some reaction intermediates that we couldn't see otherwise. And so we added parahydrogen to this thiol protected substrate shown here. So we had magnetically inequivalent positions, again, with 2 moles of the catalyst, 4 atmospheres in deuterobenzene at room temperature. Shown here is the proton NMR spectrum at the 45-degree pulse. You can see the antiphase signals. We also obtained the OPSI NMR spectrum, proton NMR spectrum as well. And from this, we could really obtain the coupling constants for the product at 13.4 hertz. And so this coupling constant is consistent with the cis hydrogenation product shown here. If it was going to be transhydrogenated species, it would be up greater than 20 hertz. And so what this helped us rule out is that we are not going through transhydrogenation. We're actually doing cis hydrogenation and then trans isomerization with this catalyst. And so I think we've been able to show thus far that, you know, we do have functional group tolerance with this. We have pairwise transfer, but are we able to actually transfer that polarization to a carbon nuclei or perhaps a carbonyl or an N15 nuclei? And so following the work of Francesca Ranieri, we really looked at this reaction that they had published in 2015 where they took ethyl acrylate, reacted with the catalyst, parahydrogen, and acetone D6. And we did this at 37 degrees C to show that we could hydrogenate the species and then hopefully transfer that polarization to the C13 nuclei. So I always liked, and I apologize to this set of audience, but I phased these NMRs for my synthetic and organic chemistry crowd, and then I couldn't go back and get the other ones. But here's the carbon-13 NMR spectrum of the product. This is a 500 millimolar sample, one transient, to really gain an understanding of how little you can really see in that carbon NMR. However, when you have the rhodium catalyst that was used to hydrogenate the ethyl acrylate, when you take that and you run the reaction, you obtain this proton or this carbon-13 NMR spectrum here. Again, it's a single transient, and you can see that the polarization transfer to C beta, C alpha, as well as the carbonyl. And so we were really curious in our hands if the cobalt complex would do the same sort of polarization transfer. And so at 64 millimolar, again, one transient, following the same conditions as we did with the rhodium, we utilized our cobalt species in the same types of reactions. And you can see that we do see polarization transfer based on this carbon-13 NMR spectrum. So here we have C beta, C alpha, as well as the carbonyl. And it compares quite nicely with polarization transfer of the carbonyl compared to the rhodium. And so these are non-optimized conditions, but it showcases that our cobalt catalyst can do polarization transfer. Since then, we have really kind of tried to expand on the substrates that our complex is capable of enhancing the signals of various olefins shown here. And so you can see in many of the substrates, we do see polarization of both in the proton and carbon-13 channel, as well as we see polarization transfer to the carbonyl, so the CO functionality. I think what's interesting is when we don't see polarization transfer or polarization of the C13. So in this case, with this alcohol species, we think that actually the alcohol reacts with our cobalt catalyst. And so while we can hydrogenate and see that hyperpolarization in the proton channel, we don't think that we can do it otherwise. In a substrate like this, shown here where we have more steric bulk, I'm not quite sure why we're not seeing polarization transfer to the carbonyl, but again, I think steric bulk probably in our system with this very bulky ligand around this cobalt center probably does play a role in some of our reactivity and what we're observing. And so we're able to do this with our cobalt complex, but we were curious if we could actually look at some other reactivity. And so we wanted to see if actually we could look at SABRE with our cobalt complex. Can we use our cobalt complex as a SABRE catalyst? And in particular, with these nitrogen containing complexes that so many have shown throughout this entire conference. What's unfortunate for us is with our cobalt species, we do have pyridine bound. And so we ran the reaction where we took 64 millimolar, we added 64 millimolar of pyridine, parahydrogen, and D6 acetone at 37 degrees C. And unfortunately, we do not see any SABRE of that purity. And so Simon Duckett mentioned it really does matter what ligands are around your metal center and where things bind. And we absolutely agree with that observation. So with our cobalt pyridine complex, we have a crystal structure of this, and the pyridine actually binds trans to that aryl moiety of the ligand scaffold. And so we also think that this is the binding site for the parahydrogen or hydrogen in general, that it needs to be trans to that aryl moiety so that you can actually cleave that HH bond and form this species shown here on the right. And so because that's where pyridine binds and it actually forms a pi complex with these flanking aryl ligands, we think that we have competitive binding of the nitrogen-based substrates with H2. And so that's why we're actually not able to do SABRE with nitrogen-containing substrates in this system. However, if you remember the proton-NR OPSI spectrum that I showed earlier on in this talk, what we did observe was perhaps SABRE of the styrene. And so we were curious if we could look at that in more detail and see that we can show SABRE with olefins in this system with this cobalt catalyst. And so Safia, Mohammed, my student, took 4-fluorostyrene, 64 millimolar, used our cobalt catalyst, parahydrogen, and observed this proton-NMR spectrum, one transient, where she introduced the parahydrogen at about 50 Gauss. And what you can see is we see both resonances hyperpolarized for the olefin, as well as we do observe some hydrogenated product. We do know we can hydrogenate olefins with this. And in this signal enhancement in the proton channel is about an 80-fold signal enhancement. And so we are able to see SABRE with this complex, with this catalyst. Looking at the polarization lifetime, it's around 2.3 seconds. But what my student did notice in this one is the fact that we have this inverted H2 peak. And I think we've seen a couple discussions about inverted dihydrogen either yesterday as well as today. And so this was interesting to us, and we looked at it a little bit more. And what we discovered is the signal for the polarized, what we think is orthohydrogen, gets very large upon our second shake. So we've talked a lot about shakes during this conference. And so this is when we take it back out and actually shake it back up and put it back in for the second round. And we can see the polarized orthohydrogen in our second shake. It decreases over time, but it's very significant early on. And we think that may be just because there's more H2 in solution than perhaps the olefin at that time. And so you're actually seeing that. But when we were thinking about this, we were curious how this was actually working with the mechanism for our various reactions. And so what we think happens, but before I get to that, we see this in a variety of substrates. So not only do we see this in 4-fluorostyrene, where we see this inverted H2 peak, we see it in 4-methoxystyrene, styrene as well. And then this pyridine containing olefin is quite interesting because we see this peak here, again, of likely polarized orthohydrogen. And we're trying to gain a better understanding, but this isn't just something we've seen once. We've seen it several times in our system. And so what we think is happening in our system is we know we have a reversible process, right? We know that olefin can come on and off. We know it can get hydrogenated based on our Altadena studies. But here what we think happens is because the hyperpolarized the parahydrogen pops on and off, we're forming orthohydrogen solution, which then in this middle species, you can see that would then bind to the cobalt catalyst with the cobalt dihydride. So you have a cobalt dihydride dihydrogen complex where the dihydrogen is ortho, the dihydride is para, and now you pass that, you polarize that orthohydrogen. And so that's how we think that this is happening, that you're going through a cobalt dihydrogen dihydride species. And we have some evidence of seeing that actually in one of our OPSI spectra. So we can also do SABRE. We can polarize on the C13 channel. So shown here is, again, a 64 millimolar solution where we see about only 38-fold enhancement in the carbon-13 channel. Again, this is not optimized. We can also observe polarization in the F19. So we see about polarization transfer over 7 bonds to the fluorine in the fluorine NMR spectrum. And so shown here is both of the olefin, and then we also do see the hydrogenated product here in the fluorine NMR. We can do a variety of substrates. So isoprene is another example for us where we can see the SABRE. And here in the proton channel, we can see the proton NMR, we see about 130-fold enhancement of isoprene with our cobalt catalyst. You can see all of the appropriate resonances for that isoprene, even the methyl CH hydrogens as well. We can see that polarized. This one is much better in the C13 channel. We see about 100-fold enhancement of isoprene in the C13 channel, so you can see that here. And so this is pretty good for us. We're able to see a variety of olefins. My student has really expanded on this to a variety of substrates. She's really done it. She's really worked hard at looking at this. And so we can do a variety of styrenes, both in the proton, the carbon. With 4-fluorostyrene, we can do the fluorine channel. Some very bulky substitutes we see in the proton. Here we also see in the carbon-13 channel that we can hyperpolarize. So shown in green is the carbons that we can hyperpolarize in these species compared to the carbons that we can't in black. We can hyperpolarize acrylates and pentanoates, excuse me, shown here, as well as terpenes like the isoprene that we showed. And so we're up to about 150-fold enhancement in the proton channel for specific substrates and about 100-fold enhancement in the carbon-13 channel. And so this is really exciting for us. I think we've been able to demonstrate with our cobalt catalyst that we can think about how we can build new catalysts, both for hydrogenative and non-hydrogenative PHIP. And thinking about the ligand design, and thinking about the cobalt, we can see a significant enhancement both in proton and carbon channels, with SABRE being up to 150-fold in the proton and 100-fold in the C13. And I'm pretty excited about the fact that we can transfer that polarization over 7 bonds in the fluorine NMR spectrum. So with that, I need to thank the students that did the work. So Keenan Takmik was the original student that started working on this and looking at the mechanisms and using parahydrogen. He passed that off to Safiya, and she's really done a fantastic job looking at the SABRE, as well as with 2 undergraduates. I need to thank Boyd as both my moderator today, but more importantly for all the discussions we've had about SABRE and for the collaborations with us. Ling Young, Zhu did all of our NMR. She did the pulse sequences, and I was lucky enough that one of my colleagues just a floor below actually had a parahydrogen generator, so that's what made this actually very easy for us. I need to thank the funding, and thank you very much for listening to this work.
Oh, that's awesome. Thank you very much for the talk, Alison. And as you might guess, we have about 1,000 questions. We're not going to have time for all of them, so this is going to have to go to the Slack. But I will ask you as soon as I can find where to start. Let's see here. First, question regarding the observed SABRE alongside PHIP. Do you think that there is scope for rhodium catalysts to facilitate SABRE if both iridium and cobalt ostensibly can do it?
So I will say we have tried to make the rhodium and iridium complexes with our CCC ligand, and the rhodium doesn't work with that ligand. We don't see SABRE. I don't know why, and I don't know what the issue is, but it doesn't work.
So in principle, but not with this structure.
Yeah, in principle, but not with this ligand set.
Next comment, nice talk. What is the method of polarization transfer to carbon-13 that you've used? Does it involve magnetic field cycling? And if so, is it optimized for different molecules? So
we do not do magnetic field cycling, and it's not that optimized. We do change things around for each molecule, but yeah, this whole system needs to be could be optimized a lot further to get much better enhancements. I think, Boyd, you've told me that a lot of times. So
right, yeah, there is one example where a magnetic shield is used, but there's no.
I didn't even present that actually, those numbers. So
right. So, right,
That's
but
okay.
it's not optimized is right. Yeah, okay. Let's see. Right, we asked that. Any idea what could be the rate determining step in the presented mechanism?
Oh, the problem with that mechanism, you saw everything's basically reversible. So we haven't actually calculated the rate determining step with like computations, but it's probably actually HH bond cleavage is probably our slow step, because I think the reductive elimination is relatively fast based on what we're seeing, especially in our alkyne studies where we have to have, you know, the way that that reacts. I think it's probably HH bond cleavage is probably rate determining, but I have nothing to back that up. I will be honest.
Gotcha. Next question, a practical one. How air sensitive and or water sensitive are these particular cobalt complexes?
So the cobalt-3 complex is air stable, the pre-catalyst, and you can reduce that in situ to the cobalt-1. But after that, that cobalt-1 is air sensitive, so and definitely not water stable. So that's something that we've actually talked about, how we could actually do this so we could have a water stable catalyst that maybe we could put in micelles or something that we could actually get. So that's something that we're interested in, but not with this system currently.
What do you think is limiting the polarization?
I don't know. Boyd, what do you think is limiting the polarization?
Well, certainly what's limiting heteronuclear polarization is non-optimal conditions, I would say, is one thing.
Right, and we know they're not optimal conditions.
Yeah. What about, for example, do you know for a fact that you don't have any paramagnetic impurities in solution with this catalyst and its level of your ability to purify it?
I mean, we purify fairly well, and we don't see, based on EPR, a paramagnetic species when we do this. So I don't know if there's paramagnetic impurities, but based on that, I would say no. But that's always a possibility, right? I mean, it can access cobalt too. So if the catalyst were to die over time, which it could be forming a paramagnetic species, but that is a possibility.
Here's a long question for which there will be very little time to answer it, but I think it's a great stepping off point for the Slack conversation. Can you be sure it is a SABRE mechanism and not a pairwise replacement of H2 like Bargon introduced in 1996? Have you studied the field dependence of your SABRE? Is 40 Gauss your 1H maximum? And why no sheath for heteronuclei? Of course, we answered that last bit. But so I guess at
we
least
can definitely answer that over Slack.
Yeah. Okay. All right. So that's a lot
that's a lot of talking and a lot of typing, so we'll take care of it.
That's right. And there are even more questions after that. So if you didn't get your question answered, please translate your question over to the Slack, and Alison and others can start addressing that at their collective leisure. Meanwhile, I will now say thank you again to Alison, and we'll move on to our next speaker.